Welcome to this lesson on non-reciprocal forces in driven soft and active matter. This is a fascinating area of modern physics that challenges our intuitive understanding of Newton's third law. Let's start by reviewing what we learned in classical mechanics. Newton's third law states that for every action there is an equal and opposite reaction. Mathematically, the force that particle A exerts on particle B is equal and opposite to the force that B exerts on A. This is called reciprocity. Imagine two particles interacting. In classical mechanics, if A pushes B to the right, then B pushes A to the left with exactly the same magnitude of force. But what happens when this fundamental symmetry is broken? What if the force from A on B is not equal and opposite to the force from B on A? In certain systems, we encounter non-reciprocal forces, where the interaction between particles violates the simple reciprocity we expect from Newton's third law. You might ask, how can Newton's third law be violated? Isn't it a fundamental principle of physics? The answer lies in what we choose to observe. When we focus only on certain particles and ignore their surrounding medium, the effective forces between those particles can appear non-reciprocal. Let me describe 4 important physical systems where non-reciprocal forces emerge naturally. First, driven colloids. These are microscopic particles suspended in a fluid and subjected to external driving forces such as electric or magnetic fields. Imagine colloidal particles in a fluid with an external field driving them. When particle A moves, it creates a disturbance in the surrounding fluid that affects particle B downstream. The key point is that particle A creates an asymmetric wake field in the fluid. Particle B, sitting in this wake, experiences a force that depends on A's motion, but A does not equally feel B's influence. Second, dusty plasmas. These consist of micron-sized charged dust particles suspended in an ionized gas with flowing ions. In dusty plasmas, charged dust particles are immersed in a flow of ions. The upstream particle shadows the downstream particle from the ion flow, creating an attractive wake force. The ion wake creates directional screening. The force from the upstream particle on the downstream one is not balanced by the reverse force because of this asymmetric ion depletion region. Third, chemically active droplets. These are tiny droplets that propel themselves by releasing or consuming chemical species, creating concentration gradients. Active droplets create chemical gradients around themselves. One droplet might release a chemical while another consumes it. This creates asymmetric phoretic flows that lead to non-reciprocal interactions. The chemical gradient from droplet A modifies the environment that droplet B experiences, but the reverse interaction is different because the gradients are not symmetric. Fourth, bacterial suspensions. Motile bacteria like E. coli swim by rotating their flagella, creating complex hydrodynamic flows in the surrounding fluid. Bacteria generate forced dipole flow fields. A bacterium-pushing fluid creates a far-field flow that affects other bacteria asymmetrically depending on their relative orientation and position. Now let's discuss what happens when we coarse-grain our description. This is where the apparent violation of Newton's third law becomes clear. You might wonder, if momentum is always conserved, how can we have non-reciprocal forces? Doesn't this violate fundamental physics? The answer is no. Momentum is still conserved when you account for the entire system, including the medium and any external driving forces. The total momentum of particles plus medium changes only due to external forces. Microscopically, Newton's third law still holds. The key insight is that the medium carries hidden momentum. When we trace out the medium's degrees of freedom to focus only on the particles, we obtain effective interactions that are non-reciprocal. In the coarse-grained particle description, the force from A to B can be much larger than the force from B to A. The momentum difference is carried by the medium, which we've integrated out. Let me write down the mathematical structure of non-reciprocal forces more precisely. The effective force on B from A is not equal and opposite to the force on A from B. This is the hallmark of non-reciprocity. We can also express this through interaction matrices. The coupling strength J from particle I to J is not equal to the coupling from J to I. The interaction matrix is asymmetric. Non-reciprocal interactions break detailed balance and time reversal symmetry. The system can exhibit perpetual currents and fluxes, even in equilibrium-like steady states. Let me work through a specific example with driven colloids to make this concrete. Consider two colloidal particles in a driven system with an external velocity field. Particle 1 on the left creates a wake that extends downstream. Particle 2, positioned downstream, sits in the wake of Particle 1. It experiences an additional force due to the disturbed fluid flow created by Particle 1. Crucially, Particle 1 does not equally feel the influence of Particle 2 because the wake structure is asymmetric. The flow primarily extends downstream, not upstream. The force on Particle 2 from Particle 1 has two parts, a symmetric potential interaction and an asymmetric wake contribution. The wake force has no counterpart in the reverse direction. What are the physical consequences of having non-reciprocal interactions? They are quite dramatic and counterintuitive. First, non-reciprocal systems can spontaneously form traveling waves in rotating patterns, even without any explicit symmetry breaking. Second, these systems cannot be described by equilibrium statistical mechanics. There's no free energy that the system minimizes. Third, you can have persistent currents and flows in steady state without any net energy input at the coarse-grained level. For example, particles with non-reciprocal interactions can spontaneously organize into rotating rings or vortices, where each particle follows the one in front. Fourth, non-reciprocal forces can lead to odd elasticity, where the stress-strain relation has antisymmetric components, fundamentally different from ordinary elastic materials. Now let's discuss how non-reciprocal interactions can be engineered to create programmable metamaterials with unprecedented functionalities. You might ask, why would we deliberately engineer non-reciprocal interactions? What advantages do they provide? The answer is that non-reciprocity provides built-in directionality. This allows materials to have different responses depending on the direction of applied forces or signals. The first major application is directional wave propagation. We can design materials where mechanical or acoustic waves travel in one direction but not the reverse. Imagine a chain of particles with non-reciprocal couplings. A wave can propagate from left to right but is blocked when traveling from right to left. This creates a mechanical diode. This one-way wave propagation breaks time reversal symmetry locally in the material, even though the microscopic dynamics might still be time reversible when including the environment. The second application combines non-reciprocity with topological mechanics to create robust edge modes and protected transport. Non-reciprocal interactions can drive the system into topological phases, characterized by complex valued energy bands and non-Hermitian topology. The effective Hamiltonian is non-Hermitian. H is not equal to its conjugate transpose. This leads to complex eigenvalues and unconventional band structures. The third major application is creating materials that can autonomously reconfigure their shape in response to stimuli. A metamaterial made of unit cells with non-reciprocal actuation can reconfigure from one shape to another, following programmed pathways that depend on the direction of applied stress. Each unit cell responds differently to forces from different neighbors. This asymmetry allows complex collective transformations that wouldn't be possible with reciprocal interactions. The fourth application is in soft robotics, where non-reciprocal materials can enable locomotion and manipulation without complex control systems. A soft robot with embedded non-reciprocal elements can generate directed motion. Sequential activation of non-reciprocal couplings creates a traveling wave that propels the robot forward. The beauty is that the directionality is built into the material it's. You don't need complex neural networks or feedback control to achieve directed locomotion. Let me describe some experimental systems where non-reciprocal interactions have been successfully realized. Researchers have used optical feedback to engineer non-reciprocal forces between colloidal particles. Cameras track particle positions and modulate optical tweezers to create asymmetric interactions. Magnetic particles on vibrated surfaces can be programmed with non-reciprocal interactions by modulating the substrate vibrations based on particle configurations. Genetically engineered bacteria with designed chemical signaling pathways create tunable, non-reciprocal interactions through quorum sensing and chemical communication. Despite rapid progress, there are significant theoretical challenges in understanding non-reciprocal active matter. Challenge 1. There is no variational principle. We cannot write down a free energy functional that the system minimizes. Standard thermodynamic concepts don't apply directly. We need new frameworks from non-equilibrium statistical mechanics. Path integral approaches and large deviation theory become essential tools. We describe these systems using action functionals that account for the irreversible dynamics and broken detailed balance. Phase transitions in non-reciprocal systems can have unusual critical exponents and scaling behaviors that differ from equilibrium universality classes. Let me give you an everyday analogy to understand non-reciprocal interactions. Think about traffic flow on a highway. Cars on a highway interact non-reciprocally. A car ahead strongly affects the car behind it by blocking the road, but the car behind has much less effect on the car ahead. The car in front constrains the following car's motion. If the front car slows down, the rear car must slow down too to avoid collision. But the rear car barely affects the front car. The front driver mostly ignores what's happening behind unless actively looking in the mirror. This non-reciprocal interaction is one reason we get traffic waves and phantom jams that propagate backward along the highway, even without any actual obstruction. Let me conclude by discussing exciting future directions in this field. Researchers are using machine learning to design optimal, non-reciprocal interaction patterns for specific functions like targeted delivery or shape morphing. There's growing interest in quantum systems with non-reciprocal interactions, which could enable directional quantum information processing and protected quantum transport. Understanding non-reciprocal forces in biological systems could shed light on tissue morphogenesis, wound healing, and collective cell migration. A major theoretical direction is connecting non-reciprocal active matter to the broader field of non-Hermitian physics. Concepts like exceptional points, where eigenvalues coalesce, and parity-time symmetry are becoming relevant for understanding phase transitions in non-reciprocal systems. Let me summarize the key concepts we've covered about non-reciprocal forces in active matter. Non-reciprocity means the force from particle A on B is not equal and opposite to the force from B on A. This emerges when a surrounding medium mediates asymmetric interactions through wake fields, chemical gradients, or hydrodynamic flows. Momentum is still conserved when you include the medium and external drives. The apparent violation of Newton's third law only appears in the coarse-grained description. Engineered non-reciprocity enables programmable metamaterials with built-in directionality for applications in robotics, waveguiding, and autonomous reconfiguration. Physical examples include driven colloids, dusty plasmas, chemically active droplets, and bacterial suspensions. Properly describing these systems requires non-equilibrium statistical mechanics since there's no free energy to minimize.